In this section, we're going to talk about numeric types. Numeric types are variables that store numbers, in contrast to Boolean types, which store true or false values, character or string types, which store printable text, readable text. Numerics store numbers, either integers or floating point. And from algebra, we know an integer is all of the information to the left of the decimal point. No decimal point, nothing to the right. No decimal portion, no partial amount. Whereas a floating point number is the left-hand side, which is the mantissa, the decimal point, and the right-hand side, which is the decimal portion, which represents a fraction of a whole. Because all values, all numbers, all information stored in a computer are numbers, we have to interpret anything other than small non-negative. Everything has to be interpreted in some standard way. For example, the floating point numbers are encoded. There's a certain number of bits for the mantissa, a certain number of bits for the exponent. There's no inherent reason why those choices are made. They're convenient and they become a standard. And the standard is called the IEEE 754. It just says how to interpret the bits. Some other scheme could have been chosen. That one is the one that was. So we follow it. Every data type has 4 significant characteristics. This is true whether the data type is built into the compiler, like the types int, double, boolean, or whether you or some other programmer create data type by writing a class. A data type has, first, a range of values. Because each variable has only a certain number of bits, it can represent only a certain number of patterns, ones and zeros. As you come up with every possible combination, eventually you run out of them. And that's the limit of patterns that can be represented. We have to be careful because not any number can be stored in a variable, just a range of them. Second, we have a set of operations. These are the things that can be done on the data type. For example, an int data type represents integer numbers. We can do addition, subtraction, multiplication, and division, although I'll talk more about that later. Various other things we can do. Third, the interpretation. I mentioned that as the encoding of what those bits mean. Different choices could be made, but once they're established, we follow them. As I've said, floating point numbers have a certain number of bits reserved for mantissa, a certain number reserved for exponent. In fact, bit is set aside for the sign bit, that is positive or negative. Fourth, we have memory size. Rarely is this a concern to Java programmers. In the C and C++ days, it definitely was a concern. This is handled by the compiler, but the programmer does need to know that certain data types have a limited range of values. Other data types are larger or smaller, so they have either a bigger range or a much smaller range. For example, the byte holds 256 different patterns, whereas the int holds approximately 4.25 billion different patterns. Int takes 32 bits. Long data type is twice that, so there's 64 bits. It obviously holds a much larger range of numbers. In the floating point numbers, the simplest one is float. It takes 32 bits. A double precision version of that is called double. That's the one we will use in this course almost exclusively for representing decimal portioned numbers. Since a type represents a specific range, we need to standardize on the ones we will prefer to use. In this course, we will use int and double. It doesn't mean that those are the only possibles. It just means that we will use those in preference to anything else. This keeps our reasoning about numbers consistent. Other types I've mentioned, byte and long, these are different sizes for integer data types. And again, integer has no decimal portion whatsoever. If we need to use a data type other than these, we'll make a point of it. Otherwise, just assume int for all integers and double for all floating point numbers. In this course, we're not going to use more exotic input and output. We're going to use keyboard and console. We need to learn how to input data from the keyboard for numeric types. The scanner class provides methods to input an integer or input a double. It handles all the nuances of signs for negative numbers, decimal points for the double data type, etc. The input will be validated to ensure that it is a legitimate integer or floating point number. Operators represent the set of operations that can be done on a variable or literal of a specific data type. Arithmetic operators, addition, subtraction, multiplication, division, are common. Less well known is the modulus operator. It is meant to retrieve the remainder of a division. If we're doing integer division, we get the quotient when we use the division sign. If we want that remainder, we use the modulus operator. Let's bring up the nasty math here. We are working on a computer. It is limited in what it can do. Computers do not represent mathematical concepts as precisely as a mathematician. It's because we have a finite amount of bits available to represent numbers. That means our range is very small. Integer division is something that catches every programmer many times. We must understand integer division returns no decimal portion. Thus, 10 over 3, which we instantly understand to be 3.33 continuing, we would get the answer 3, no decimal portion. This is where the modulus operator comes in. If we say 10 divided by 3 results in quotient 3, but what's the remainder? We would do 10 modulus 3, and it would return 1. So the answer would be 3 goes into 10 3 times with a remainder of 1, but we would have to do it in 2 operations, one the division and one the modulus. I have a habit of saying div when I do integer division to try to help my mind remember that I'm going to get no decimal portion. If we need that decimal portion, use a double. Here's some more nasty math. Integers are closed under addition, assuming we don't exceed the range. What that means is, if we add an integer to an integer, the result is an integer. Mathematicians call that closure under addition. Ints also are closed under multiplication, but again, as long as we don't exceed the range. Here's something odd. The largest integer, 2.14 billion, notice it ends in a 7. If we add to it, our minds would think simply that will be blah, blah, 8. Well, it is. Unfortunately, notice that it says negative 214 blah, blah, 8. What happens, in fact, is that the numbers loop around. Let me see if I can show you that. I'll just use very tiny numbers. 8, 9, 10. If we added one more, we would expect 11. But the way this would actually work is it would go negative 11, negative 10, negative 9, negative 8, dot, 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 0 over here somewhere, 1, 2, dot, dot, dot. It's circular with this junction right here. The maximum integer and the minimum integer happen to be next door to each other, and it just loops around this ring. This is a limitation of a machine. You and I would naturally think this, a mathematician would bark at it, because that's not the way it's done in reality, but it is the way it happens in a computer. So we have to allow the fact that our ranges are limited and we can't exceed them. Taking the maximum integer and adding 1 to it gives us the minimum integer, and that is not intuitive. We would not expect that, but it's real, so just beware. Integers are not closed under division. Said a different way, that means an integer divided by an integer does not always yield an integer. We might say 10 divided by 2, result 5. That's an integer, great. But what about 10 divided by 3? We don't get an integer result. We get an integer quotient, and we can get an integer remainder, but the real number that comes back is not an integer. Doubles, which represent mathematical real numbers, are closed under addition and multiplication because any such operation on them returns a double, again, as long as the range is not exceeded. And finally, exponentiation, raising a number to a power. Java does not provide an operator to do this. Java does, however, provide a library call from the math package called pow for power. We would say math.pow parentheses, and then we give the base. For example, 2, and then a comma, and then the exponent, let's say 3. The result would be 2 to the 3rd power, or 8. The result comes back as a double number, so technically it would be 8 0.0. To determine the area of a circle, we could easily say math.pi, that's the constant that represents the value of pi, times math.pow radius, 2, and that's pi times radius squared.